All right, on to section 5.2. So we talked previously about the concept of area under a curve, okay, an area under a curve representing accumulated change or total change in a quantity, particularly distance we looked at, or population growth. So here we're going to define the definite integral. So suppose f is continuous for a to b. When we say continuous, it just means there's no holes, no gaps in the graph. It's kind of a normal connected graph. The definite integral of f from a to b, which is written in the following way. So this is like this. So we have the integral from a to b of f of t dt. Okay, this is the limit of the left-hand or right-hand sums with n subdivisions of AB as n gets arbitrarily large. So in other words, before we were taking rectangular approximations, right, we were making a bunch of rectangles, using them to get a pretty good idea of what the area was. The concept of the integral, the definite integral, says for the interval from a to b, I'm going to subdivide it n times, but n is going to get infinitely large. So I'm going to have 100 rectangles, then 1,000 rectangles, then 1,000,000 rectangles, then 1,000,000,000 rectangles, etc., etc. N just keeps growing and growing and growing. And as n gets larger and larger and larger, the rectangles get closer and closer and closer to the actual area under the curve. So what the definite integral is giving us is this area under the curve. So just a couple notational things here to take note of. So this function inside of the integral, this is what's called the integrand. Okay, so the integrand is just the function inside the integral. Okay, whatever that is. In this case, it's f of t. And then these values here, so the a and the b, these are what we call the limits of integration, but more commonly we'll just call them bounds. So the bounds of the integral are a and b. So that tells us how far we're going on this interval. Okay? So in the example from the last section, so in the bacteria example that we had, where we saw a bunch of different approximations, what we found was the more rectangles we used, the larger our value got, because it was getting closer and closer to the actual area under the curve. So the value, the integral from 0 to 20, so over the first 20 hours of f of t dt, the function in question, if you go back and look at those notes, the function was 3 plus 0.1 t squared dt, 0 to 20. Okay, and I should mention the dt, this term here, so the dt, all this is really doing is just indicating what variable we're integrating with respect to. So you do need to include it when you're doing integration. That's a common error. People forget to include that, but it is important that it's in the integral because it's indicating what variable you're using. Okay, so here we have our integral of 3 plus 0.1 t squared dt from 0 to 20, and we saw in the previous section when we did this example that this was approximately 307 million bacteria, right? That was the closest approximation we got, was 307 million. Okay, and so what we are doing now is with this curve from 0 to 20, we're taking so many rectangles that we're just basically filling in the entire area here. Okay. So our best approximation at this point was 307 million, just because that's the rectangles that we used. Okay. So let's look at this next example down here. So values for f of t are given in the table. Estimate the integral from 20 to 30 of f of t dt. So in this case, we're trying to estimate the value from 20 to 30 of this function. So in order to do that, we're going to get an overestimate, get an underestimate, and then we'll go ahead and average them together to get something a little bit closer. So let's go ahead. We already have the values, right? So we've got all of our outputs, and we can look at that distance, right? How much change is occurring over these intervals. Okay, so this, it looks like our delta t is going to be 2 in this case. Okay. And our number of subintervals is going to be, so from 20 to 22, so that's 1, 2, 3, 4, 5 subintervals. So it looks like we have n equals 5 in this case. Okay. So let's go ahead and let's get the left-hand sum first. So we're going to add up all of the areas of each of these rectangles using the left-hand endpoints. So we're going to have 5 times 2, plus 7 times 2, plus 11 times 2, plus 18 times 2, plus 29 times 2. Okay, and we're not going to use the last one because, again, we're only using the left-hand side of each interval. But this is going to give us 140. Okay. So we don't necessarily know if this is an underestimate or an overestimate. We'll find out when we do the other one, because one of them is going to be too big and one of them is going to be too small. Okay, and it can change which one is which, but it's a guarantee they won't both be under or both be over. It'll always be one is over, one is under. Okay. So for the right-hand sum, now this time we're using the right-hand endpoints of each interval. So I didn't write the formal version in the first case, but let me go ahead and do that now. So this is going to be f of 22 times delta t plus f of 24 times delta t plus f of 26 times delta t plus f of 28 times delta t plus f of 30 times delta t. Okay. So this gives us, what, 7 times 2 plus 11 times 2 plus 18 times 2 plus 29 times 2 plus 45 times 2, which is 220. Okay. Now, one interesting thing I do want to point out here, notice when we were doing these sums, the left-hand sum, right-hand sum, all the values except for one, except for the first one here and the last one here, all those other values are the same. And that's because those values serve as the left-hand endpoint of one interval and the right-hand endpoint of another interval. Okay, so your calculation is going to be almost the same, just with one slight difference. Okay, so in this case, we have our left-hand sum is the underestimate, and the right-hand sum is the overestimate. Okay, so I know that the actual area is somewhere between these two, okay, but we're going to go ahead and get a better estimate. And we're just going to do that by taking an average. Okay, so by averaging. Okay, so that's going to be the integral from 20 to 30 of f of t dt is approximately equal to, so that's 140 plus 220 over 2, which is 180. And with data points like this, that's pretty much the best we can get. So we go ahead and say that this is as good an approximation as we can get at the moment. Okay? And we'll see again in the future how we'll be able to get better approximations.